So this video is for the assignment, What Affects Phase Changes? The day we did this assignment in class, I did a series of demonstrations that went along with this assignment, but upon consideration, I decided to be very difficult to record those demonstrations and give the lecture information all in one video and be able to show all of the intricate details that you could see in person for those demonstrations. So this video, sadly, is only just going to contain the lecture information and not the demonstrations, okay? So if you start off on the assignment, the first slide has a couple of questions about the temperature at which water boils. The first one says, what temperature does pure water boil? The second one is, what temperature does salt water boil at? If you are familiar with this, pure water at sea level and in my classroom today was boiling at 100 degrees Celsius. The salt water, however, was boiling. We had a beaker of salt water that was boiling at 108 degrees Celsius. Okay, so a little bit warmer. Now, the next question asks, why does salt water boil at a different temperature? Now, this has multiple reasons. Well, not multiple reasons, but it has a longer explanation. And it starts with understanding, remembering the different ways that atoms bond together to form molecules. If you remember, there are two different forms of these bonds. There are covalent and ionic. For this, we need to remember the ionic bonds. If you remember, an ionic bond is one where there is a transfer of electrons. Okay? And the example that I had given when we talked about ionic bonds was sodium chloride, NaCl. And sodium chloride is salt, or table salt specifically. Okay? And in this example, when you put salt in water, it will break apart into its different ions, is what they're called, and you'll have this chloride or chlorine ion and a sodium ion. Okay? Now, they both have their charge, sodium being positive, chlorine negative, and if you remember, water itself has a charge. Okay? It is not a neutral molecule. So water has a region where it has a positive charge and a region of a negative charge. And so, as you might expect, the chlorine is then attracted to this positive region and the sodium to the negative region. Okay? So, we'll draw these on here. So we've got a sodium here, a chlorine down here. Now, these are very strong attractions. Strong enough, in fact, that they'll begin to attract other water molecules. Okay? And so these other water molecules begin to also interact with the chlorine as well as the sodium. Okay? And the salt, the sodium and chlorine, these ions, they will hold tightly to these molecules, kind of holding them close together. And if you remember, the different phases of matter are partially determined by how close or how far away different molecules are from one another. And so in this instance, the molecules stay close enough together that they are more difficult to separate to become a gas. And so therefore they require more energy in order to become a gas. And the boiling point is higher, okay, because temperature is a measurement of heat, how hot something is, and heat is a form of energy. So we can say that temperature is a recording of how much energy something has. And so in this instance, because these different substances are in a way kind of glued together, it's more difficult for them to separate and become a gas. Okay? All right, moving on to the next slide in your assignment. So the next slide talks about a vacuum chamber. Now, you may have been familiar with vacuum chambers before. They're very popular on YouTube. If you're not, what a vacuum chamber does is it's a closed container that has a vacuum attached to it. So let's say this is my vacuum engine. I apologize, I'm not much of an artist, but this is my vacuum engine, and attached to it is a hose that, for my vacuum chamber, attaches to a platform. and that platform has a dome over it, and this vacuum sucks the air out of this dome and creates an area with little to no air in that. It travels then out through the hose and into the vacuum, okay? And so that's what a vacuum chamber is. The next thing we did in class is we put a beaker with water in that vacuum chamber, and then turned on the vacuum chamber, removing the air from around the water, and observed as the water boiled at a different temperature. Okay, so to kind of model this, for you to visualize it, we have a beaker here. That beaker contains water. Okay, these little water molecules throughout it, right? And if you remember, molecules in liquids and gases and atoms as well, as they move around, they move very erratically, right? They have no control over where they're moving, and as they move, they end up hitting against these walls of the beaker and create a force there on the walls of the beaker and on the surface as well. Now, if you remember from yesterday, we asked the question if a glass is half full or half empty, and we determined, well, glass is always full, right? Because here above, we have gas as well, okay? So the glass is full of gas as well. And that gas, it's applying forces, okay, because it's moving around, and it applies a force on the water. In fact, the gas is even outside the beaker, applies forces to the outside of the beaker as well, okay? Now, as we then introduce a vacuum chamber, the vacuum chamber will then remove these gas particles. And in doing so, it removes that opposing force to the water. And so we end up seeing that water then begins to boil at a very low temperature. In fact, in class, it was boiling at 19 degrees. Okay, so we had the water boiling at 19 degrees Celsius. And it does that because it no longer has this opposing force, it doesn't have this force anymore opposing the water, and so instead that water begins to spread out and become a gas, okay? Now, what I'd love for you to do is to pause the video and answer the questions on slide 3, which are, what can we learn about things in a vacuum chamber? And if you had a vacuum chamber of your own, what experiment would you like to try? So pause the video, answer those questions, and then come back and we'll discuss the hot pads. So on slide 4, our last slide, I have some interesting hot packs. They're what are called rechargeable hot packs. And they're a little bit different from a normal hot pack. If you remember a normal hot pack, you remove from the package, and you may shake it around, and it interacts with the air around it and begins to heat up. Okay, it's a chemical reaction that occurs, and as that chemical reaction occurs, it releases heat. My hot packs, however, are a liquid. Okay, inside we have a liquid. And in that liquid, there's a little disc, and when you snap that disc, it transitions that liquid and freezes it. It begins to become a solid, okay? Now, if you remember, in order for a liquid to become a solid, we have to actually lose energy. We need to take away energy, okay? So these hot packs are actually freezing. They're in the process of freezing, which is changing from a liquid to a solid. But in order to freeze, they actually have to lose the energy, which is why they're hot. They're hot because they're giving off energy. That energy is kind of being emitted from it while it's transitioning into a solid. Once it's fully frozen, it's fully a solid, it's back to room temperature, and no energy is being released. Okay? This lecture, I apologize, definitely wasn't as fun as actually being here, doing these experiments, seeing them in person, but at least it's something to help you to work on this assignment. If you have any questions, as always, feel free to send me an email, and I'll help you as best as I can.